So good morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. So today we are going to discuss about the electric dipole. Electric dipole. In the previous class, the last class, we discussed about the energy density in electrostatic fields. Energy density WE is equal to 1 by 2 the integral of minus infinite to infinite E bar dot D bar into D, the volume integral. Now today we are going to discuss about the electric dipole. An electric dipole. See the diagram here. The field due to an electric dipole, field electric field intensity. The two point charges of equal magnitude but opposite signs. You can take on the positive z axis a positive charge Q on the point A on positive z axis. At the point A, you can choose a positive charge Q, and in the negative z axis at the point B, you can take a negative charge minus. The 2 point charges of equal magnitude but the opposite signs separated by a very small distance. A very small distance. The distance is a d. The distance is a d. Very small distance. You rise an electric dipole. You rise an electric dipole. The field produced by such a dipole plays an important role in the engineering electromagnetics. Consider an electric dipole as shown in the figure here, the 4.32. The 2 point charges plus Q and minus Q are separated by a very small distance should be. Consider a point P as a spherical coordinate system. Spherical coordinate system R, theta, and the phi. Consider a point P, R, theta, and phi in the spherical coordinate system. It is required to find out the E bar due to the electric dipole at point P. E bar, the electric field intensity or electric field strength due to the electric dipole. Let O is an origin, the midpoint of A and B. Origin is O here. It is a midpoint of AB. So the distance between A2, the distance between the A2, the origin O is a d by 2. And the distance from origin to the point B is a d by 2. Because the distance from A to B is a d. A is a midpoint. The distance of point P from A to the point P is R1 distance, while the distance of the point P is R2 distance, and the distance of point P from the origin is R, and the distance of separated by the charges is D, is a very small compared to the distance of R1, R2, and R. Compared to the R1, R2, and R, the distance from the A to B is very small, and the coordinates of R are the coordinates of A are. A is on the z-axis. A is on the z-axis. So xy, the point on the z-axis means x value is 0 and y value is also 0, and the z value is there, that is a d by 2, plus d by 2. A point plus d by 2. And B is also on the z-axis. So the x value is 0 and y value is 0. And because it is in the negative z-axis, the distance is a d by 2. That is, the sign is a minus d by 2. Okay. So these are all the distances from the origin point A and the point B, and from origin to the A and origin to the B, and coordinates on the z-axis, positive z-axis, and the coordinates on the positive, negative z-axis. Okay. To find the E bar, we will find out the potential P at a point P due to the electric dipole. Then, by using the E bar is equal to del B. You know the E bar del B is a gradient of V. Is one of the formula we have. E bar is equal to minus del. We can find out the E bar due to the electric dipole. So the V is equal to, or first of all, if I am taking the V is equal to a point charge, the potential at the point charge, the formula is a V is equal to Q by 4 pi epsilon naught R. Q by 4 pi epsilon naught R. Now I am taking the V1, the distance is a R1 distance. So the dipole is from A2 and the B2 here, that point P. Let this distance is R1 from point A and from point P R2. And that point A, the charge is plus Q. And at point B, the charge is minus. So V1 is equal to Q by, that is a plus charge, Q by 4 pi epsilon naught R1 is a distance from A to P. Similarly, if I am taking the V2, the potential is Q by 4 pi epsilon naught only A. But here, when I am considering it as a point, this is at point A, and now I am writing this at point P, V2 is equal to minus Q by, because the charge at the point P is minus Q, whole divided by the 4 pi epsilon naught, and the distance from point P to the point P is R. Got it, my dear students? So V1 is equal to Q by 4 pi epsilon naught R1 at the point A, and the potential due to the charge at minus Q is given by the V2 is equal to minus Q 4 pi epsilon naught R2. The total voltage V is equal to V1 plus V2. V is equal to V1 plus V2. The common term is 1 by 4 pi epsilon naught is a common term for the two functions. And Q is also the common term is that Q is also, for first one is 1 by R1. So the second one is a 1 by R minus 1 by R. Okay. Q by 4 pi epsilon naught is a common term for the two functions of V1 and V2. So first one is a positive 1 by R1, second one is a negative 1 by R. So V is equal to, you'll get the Q by 4 pi epsilon naught. We can write as R2 minus R1 by R1 into R. Is a potential V is equal to, we got the total potential at the point P is the sum of V1 plus V2. Okay, so see here the V is equal to Q by 4 pi epsilon naught R2 minus R1 by R1. Now the point P is located in Z is equal to 0. If now the point P is located in Z is equal to 0, the plane as shown in the figure, Z is equal to 0, then R2 is equal to R1, as we get the V is equal to 0. Okay, thus the entire Z is equal to 0 plane, XY plane is a 0 potential surface. Thus the entire Z is equal to 0 plane, that is XY plane is a 0 potential surface. Okay. All the points in the Z is equal to 0 plane behaves as similar to that of, I will take this, all the points in the Z is equal to 0 plane behaves similar to the points at the infinite as well as all are at the 0 potential. Now you can see here the 0 is the point 4.33, the point P in the Z is equal to 0 plane, and R1 is equal to R2. Both are the distance is the same. That is Z is equal to 0 plane. Now consider the P is located far away from the electric dipole. So previously, if I am assuming a point P and the distance is R1 and R2, the potential P is equal to V got. And in the second case, when R1 and R2 is both are the same, the distance from the point A and the point P to the point P is both are the same, then the voltage is a 0. Now in the third case, if I am taking the third case, R1 and R2 and R, Now consider the point P is located far away from the electric dipole. Thus, R1, R2 and R can be assumed to be the parallel. Means the point P is assumed in the infinite. The point P is at the infinite, means R1 and R2 and R3 look like it is a parallel, the far away, parallel to each other as shown in the figure 4.34. Point P is too far away, and the point P is in Z is equal to 0 plane, R1 is equal to R2, the potential V is equal to 0. V is equal to 0. So in this, when the point P is located far away from the electric dipole, thus R1 and R2 and R can be assumed as to be parallel to each other as shown in the figure like this here. Okay. Draw a line from the point A, draw a perpendicular line from point A on the R2. On the R2. See here, it is a dotted line showing that on the R2. So it is a 90 degrees. So AM to the point P, AM to the point P, and M to the point P here. In this case, only the R1 is equal to R. Because both are, it is a perpendicular line, the AM line is there, R1 is equal to R. But it is not equal to the A to the P and the B to the P. Only it is equal to the A to the P and M to the P. And P to M is R1, and you can subtract its total value, the PM plus M in MP. Okay, so the AM is drawn a perpendicular from A on R2. The angle made of R1 and R2 and R with the Z axis is the theta, as all are parallel. And these are right angle triangle now. Whenever you can draw a perpendicular line on the R2, we'll get ABM is a right angle triangle. The right angle triangle. What is a right angle triangle? Here the theta we can consider. Theta we can consider. The adjacent side is a BM. Adjacent side is a BM. And AB is an hypotenuse. AB is an hypotenuse. So like this, which is a right angle triangle showing right angle triangle. In this, the adjacent theta is here. Theta is here. The value is A and the P, and this is a M. Okay, the right angle triangle. Hypotenuse is AB, and the opposite side is AM, and adjacent side is a BM. Adjacent side is a BM here. Opposite side is AM, and AB is the hypotenuse. So what is the cos theta now? The cos theta is adjacent side by hypotenuse. What is adjacent side is a BM. Hypotenuse is a AB. So BM is equal to AB into cos theta. AB cos theta. So AB, this is nothing but this, the line is a AB. What is the distance of AB here? The length of that AB is a D. So BM is equal to D into cos theta. After drawing the line, perpendicular line A to the M, the R1 and R2 from the M to the point P and A to the point B is the same. Now after that, whenever you can draw a line, it's a right angle triangle showing the BM is an adjacent side, AB is an hypotenuse, and AM is a opposite side of this theta. Theta is opposite side here, the adjacent side is opposite side. This one is the adjacent side, and this is a hypotenuse. Okay. From that, the BM is equal to D into cos theta. Why you get the D? AB is the points, the distance of AB is a D. Got it, my students? Then, from this diagram, you see here, from this diagram, the equations will get the PB is equal to PM plus PM. We'll draw here. The line is like this, and we have a points dotted line is a M, the point B and the point A, and from the origin here, the another line, okay, is the distance of R1 and the distance of R and the distance of R2. And the point P is at the far away from the dipole. So PB is equal to, so the PB is equal to PM plus BM. Got it, my dear students? PB, and let us take it as here the point P, and here also the point P, and here also the point. Because the point P is at the far away from the dipole, so R1 and R2, and the R is showing that is a parallel lines. So PB, totally the PB is equal to PM plus BM. Okay, and PA is equal to PMO. The distance is because AM is a perpendicular line. So PB is equal to, what is a PB is equal to? PB total distance is R2, PB is equal to R2, and PA is equal to R1. PA is equal to R1. What is a BM is equal to? What is a BM is equal to? PB minus PM. What is a PB? R2 minus, what is a PM? Is R1 only. PM is nothing but a PA. Little bit confusion again. Your thing I will explain here. Here itself only. See, this is a point P. Let us take here also the P, and here also the P is there, and here also the P. Now, PB, this is a total distance. The total distance is R. First of all, if I am writing that is a PB is equal to P to M. This is a distance here. P to M, PM plus, and BM also, BM. So what is a PB distance from point B to the point P is R2. R2 is equal to, what is a PM? When you draw a line is a perpendicular line from point A to the point M, the PA is equal to PM. These both are the lines is the same. PA is equal to the PM. So PM is equal to, now I am writing this as a PA plus BM. What is the distance of PA? Is R1 now. So that implies the R2 is equal to R1 plus BM. Got it, my dear? So what is the BM now? The BM is equal to R2 minus R1. The total distance is R1. So in that distance, if I am removing the PA value is R2, so the BM value is R2 minus R1. R2 minus R1. BM is equal to. So what is a BM we got from the right angle triangle? BM is equal to d cos theta. BM is equal to d cos theta. So what is a BM now? R2 minus R1. R2 minus R1 is equal to d cos theta. What is the total voltage we got? V is equal to Q by 4 pi epsilon naught whole multiplied with R2 minus R1 by R1 and R. Okay, this is a formula we got when the point P is considered with the distance of R1 and R2 and something. So the R2 minus R1 is a d cos theta. So the potential V is equal to Q by 4 pi epsilon naught. Substitute the R2 minus R1 is a d cos theta, and denominator is a R1 and R2. So V is equal to, so the approximately we can say the V is equal to QD cos theta by 4 pi epsilon naught, 4 pi epsilon naught. When these R1 and R2 both are is equal here, in this the distance is we can consider as R, let it be the R square. So the potential, the electric dipole, the QD cos theta by the 4 pi epsilon naught R square. So actually it is a potential at the point charge is a Q by 4 pi epsilon naught R only. So it means that the V is proportional to 1 by R. The potential at the point charge V is proportional to 1 by R. The potential at the dipole is proportional to 1 by R square. 1 by R square. In the last class, we discussed the energy density in the electrostatic field. When we take the VD bar, the potential is 1 by R and the T is proportional to the 1 by R square. And totally it is a V is proportional to the total of VD bar is 1 by R cube, and it is a dot product of with the surface ds bar is equal to R square, is R cube, and R square and the 3 is cut cancelled 1 by R. When R tends to infinite, the VD bar is equal to 0. So the first term gets the 0 there. And in the electric dipole, the potential is proportional to 1 by R square. Potential is proportional to the 1 by R square. Q, D, cos theta and 4 pi epsilon naught is total, it is a constant. So V is proportional to 1 by the R square, the distance from the origin to the point P. Okay, my dear students. Now see. So V is equal to Q by 4 pi epsilon naught D cos theta by R square. As the D is very small, R1 and R2 approximately. If I am saying here it is R1 and R2 is both are not same. When R is approximately equal to the R2 and approximately is equal to R, hence R1 and R2 is R. Okay, the potential V is also the approximately the Q by 4 pi epsilon naught. Q D cos theta by the R square, the volts, the potential. Now, in the gradient of V, E is equal to minus E bar is equal to minus del V. What is the V? We got V is equal to QD cos theta by 4 pi epsilon naught R square. Epsilon naught R square. Substitute here, because it is a spherical coordinate system, minus del V is equal to minus of dou V by dou R into AR bar plus, because the differential elements it multiplied the R into d theta, dr is a differential element, R into d theta, R sin theta into d phi. So the second term is 1 by R into dou V by dou theta d theta bar, and the last term R sin theta, so 1 by R sin theta dou V by dou phi into A phi bar. Okay, this is a del V. Now take the V is equal to here and apply the derivative with respect to the R, and apply the derivative with respect to the theta here, and apply the derivative with respect to the phi. So the E bar is equal to minus of the first term here, that dou by dou R. So the remaining terms is a constant QD cos theta whole divided by 4 pi epsilon naught and dou by dou R, applying the derivative of R square. R square means you can write as R power minus 2. Minus 2 means minus 2 R power minus 2 minus 1. Okay. So R power n, the derivative is n into R power n minus 1. What is a 1 by r square means 1 by r square. The derivative is r power minus 2. So minus 2 into r power minus 2 minus 1 is the derivative of 1 by r into ar bar is ar bar plus second term is 1 by r into dou v by dou theta. The v we got is a qd cos theta by 4 pi epsilon naught r square. In this qd by the 4 pi epsilon naught r square is a constant and cos theta, apply the derivative of cos theta. Cos theta is a sin theta here and the a phi bar, not the a phi, a theta bar. And the third term 1 by r sin theta into dou v by dou phi. There is no any phi here. It's totally the constant. The derivative of dou v by dou phi is 0. Derivative of constant is 0. So there is no any third term. Okay. After applying the derivative of third term, we'll get 0. Got it, my dear friends? You see here, finally, for dou v by dou r, the term we get is minus 2 cos theta. What we get is a minus 2 qd cos theta by 4 pi epsilon naught r power minus 2 minus 1 is r cube. The first term is. And second term here, qd cos theta, not the cos theta, qd by 4 pi epsilon naught r square is there. And because it's a cos theta is a minus sin theta, sorry here, minus sin theta. And dou v by dou phi is equal to 0. Substitute all this, we get the r into r is r cube here. So the e bar is equal to, in this the function is qd is a common term, qd, and here also the 4 pi epsilon naught r cube, here also r cube is there, 4 pi epsilon naught r cube whole multiply with 2 is there, 2 cos theta into ar bar plus, not the plus, here the minus is there, minus qd is already there, the 4 pi epsilon naught r into r is r cube, and the sin theta minus sin theta a phi bar, not the a phi, a theta bar, is a final equation for the electric field intensity in the dipole. Okay, it's already, because of here it is a minus is there, and here also the minus del v. So e bar is equal to minus of all the multiplied with the minus qd by 4 pi epsilon naught r cube, 2 cos theta a r bar plus sin theta a into a theta. With the minus del v, here the minus is also there. Minus into minus is a plus, and here the minus into minus is a plus. E bar is equal to qd cos theta, not the qd cos theta, sorry, qd by 4 pi epsilon naught r cube whole multiplied with 2 cos theta a r bar plus sin theta a theta. Now in this electric field intensity in the dipole is totally, it is a constant, is proportional to 1 by r cube. Electric field intensity is proportional to 1 by r cube, and the potential is proportional to 1 by r square in the dipole. But in the point charge, the electric field intensity is proportional to the 1 by r square, because electric field intensity is a q by 4 pi epsilon naught r square into a r bar. R square into a r bar. So the E bar is equal to, not is equal to, proportional to 1 by r square, or d bar also. And potential is V is equal to, in the point charge, V is equal to Q by 4 pi epsilon naught r. So V is proportional to 1 by r. In the point charge, potential is 1 by r, or electric field intensity, or the electric flux density is proportional to 1 by r square. But in the dipole, the voltage is proportional to 1 by r square and the electric field intensity is proportional to 1 by r cube. Similarly, the d bar is also proportional to 1 by r cube because the relation is epsilon naught into E bar. Got it, Marty? So it's a very important topic, the electric dipole for electric field intensity and the potential V is equal to. This is the electric field intensity E bar at point P due to an electric dipole. E bar is equal to QD by 4 pi epsilon naught r cube 2 cos theta into AR bar plus sin theta into A theta. Got it, Marty? And next topic is a dipole moment. Dipole moment. Let the vector length directed from the minus q to the q from the point B to the A is d bar. So in the electric dipole, a point A is on the z-axis, positive z-axis, and the point B on the negative z-axis. And from the origin, the distance is d by 2 here, and the distance from the origin to the point B is d by 2. And at the point B, the charge is q, and at the point A, the charge is plus. The vector length directed from minus q to the q is a direction here. Az bar is upward direction is a az bar, downward direction is a minus az bar. So d is equal to d. And now the d is a vector in the A direction. It's the point A direction is a positive az bar. So d into az bar, having the magnitude and also the direction. Okay. Its component along the r bar direction. Component means dr is equal to d bar dot ar bar. If I am taking it as a ar bar, if it suppose the theta bar means d theta is equal to the d bar dot a theta bar is a component along the direction of ar and along the direction of a theta and so on. So the dr is equal to d bar dot ar bar, and that d bar is in the towards the direction of positive z direction, d into az bar dot ar bar. That is equal to d into, according to the vector transformation, az bar dot ar bar is a cos theta. The vector transformation, we have the matrix form is there, sin theta, cos phi, and something is there, the d cos theta. The d is a magnitude here, the az and az bar dot ar bar. By using that vector transformation, the az bar dot ar bar is equal to cos theta. In the coordinate system, we already discussed about the, here we'll get the cos theta, and sin phi, sin theta, and cos phi, cos theta, and here the cos theta is. It is az bar dot ar bar. Az bar dot ar bar. Got it, my students? It's a conversion of Cartesian coordinate system to the spherical coordinate system. Understood? So the d az bar dot ar bar is equal to, actually it is a 0, but vector transformation, by using that vector transformation, the d into cos theta. So both are the perpendicular. The az bar dot ar bar is the magnitudes and the cos theta is there. Okay, cos theta, d cos theta will get. So dr is equal to the component along the r bar, dr is equal to d cos theta. Therefore, d bar is equal to along the direction of r, d cos theta into ar bar. Then the product of qd bar is called the dipole moment. Qd bar is called the dipole moment, and it is denoted by the PR. Is equal. Got it, my dear students? So qd bar, whatever the qd bar is called the dipole moment, and it is denoted by the PR. Now I can substitute in the equation of electric field, the P bar is equal to QD bar. P bar is equal to QD bar. The dipole moment is measured in the coulombs and the meter. Now the dot product of P bar dot AR bar, the dipole moment along the direction of the R bar or PR component, simply saying that. So what is a PR? P bar is a QD bar dot AR. QD bar dot AR. What is a D bar dot AR bar here? D bar dot AR bar is D bar dot AR bar is a D cos theta. You see here. This is a D bar dot AR bar is D cos theta. Got it? So P bar dot AR bar is equal to P bar is nothing but the QD bar as a dipole moment. QD bar dot AR bar and D bar dot AR bar is a D cos theta. So QD cos theta is equal to P bar dot AR. What is the potential we got? The P is equal to QD cos theta whole divided by the 4 pi epsilon naught R square. Now we got the QD cos theta is with the dipole moment the P. So the P bar dot AR bar whole divided by the 4 pi epsilon naught R square into, it is a volts, P bar dot AR bar, means the total QD cos theta is equal. Understood, my students? And similar way, in the electric field intensity also, we got the QE bar is equal to QD by the 4 pi epsilon naught R cube, and whole multiplied with the 2 cos theta AR bar plus sin theta into A theta bar. This is a formula we got. This is electric dipole for the electric field intensity. Electric field intensity to the electric dipole. Now, in this, we can substitute the E bar in terms of the electric dipole moment. So P is equal to, if I am taking the P bar is a vector. If I am taking the P bar as a magnitude, the P is equal to P bar magnitude of, both are the P. There is no P is a scalar and the P bar is a vector. For that P bar, we can apply the magnitude, both are the scalar. That is what is a P bar is there? P bar is nothing but QD bar. P bar is equal to QD bar. It's a formula we have. QD bar. Now applying the magnitude on both sides here, it becomes of Q is a constant magnitude of the D bar. Then is equal to QD. So P is equal to QD. So that can substitute the QD is equal to the P. So E bar is equal to P by 4 pi epsilon naught R cube into 2 cos theta AR bar plus sin theta into A theta bar. So electric field intensity due to the dipole, can be expressed in terms of the magnitude of the dipole moment. E bar is equal to P by 4 pi epsilon naught R cube. Okay. QD cos theta is a P bar dot AR bar. So here, the potential is inversely proportional to the square of the distance from the dipole. I'm saying that is a V is proportional to the square of the distance from the dipole, R square, V is proportional. And the electric field intensity is inversely proportional to the cube of the distance from the dipole. So electric field intensity is inversely proportional to the square cube of the distance from the dipole. It's a single point charge is called the monopole, in which the potential V is equal to 1 by R and the electric field intensity is 1 by R square. This is a point charge, at point charge, that is called as a monopole. Now I am taking the dipole. The dipole, the potential is 1 by R square and the electric field intensity is 1 by R. At the point charge, what is the E bar is equal to? The point charge E bar is equal to Q by 4 pi epsilon naught R square into A R bar. Potential is Q by 4 pi epsilon naught R. These are the two formulas for the electric field intensity and the potential at the point charge. This is a point charge, my students. Okay. So E bar is here. E bar is proportional to 1 by R square, inversely proportional to the distance. And the potential is also proportional to the 1 by R, inversely proportional to the distance. Here, for the single point charge is called the monopole, in which V is proportional to 1 by R and the V bar is proportional to 1 by R square. When we consider the dipole means at the point A, the charge is Q plus Q. At the point B, the charge is minus Q, the dipole here. Dipole, the potential is inversely proportional to the square of the distance, 1 by R square. And the electric field intensity is proportional to 1 by R cube. Here the R square and here the R cube. Here the R and here the 1 by R square. In the dipole, and here the point charge, nothing but the monopole. Got it? The arrangement of the 2 point charges is called a dipole, in which the potential V is 1 by R square and the electric field intensity is proportional to 1 by R cube. Got it, my students? And similarly, symmetrical arrangements a large number of point charges produces a potential and the fields which are inversely proportional to the higher powers of R, such as next we'll get the R cube, R power 4, etc. Such arrangements are called the multiple poles, monopole, dipole, and then we go for 1 by R and 1 by R square. Then it becomes of 1 by R square and 1 by R cube. And the next stage we'll get it is 1 by R cube and 1 by R power 4. The potential is inversely proportional to 1 by R cube and the potential electric field intensity is proportional to the 1 by R power 4 and so on. Such arrangements is called the multiple poles, monopole, dipole, multiple poles. The symmetrical arrangement consists of the 2 dipoles, symmetrical arrangements plus Q and the minus Q and plus Q. Is called quadrupole. Monopole, dipole, multiple pole, and the quadrupole. Means it's a 4 is there. Understood? 3 we have the R cube and R power 4. Single charge, double charge, 3 charges, and the 4 charges, quadrupole. The symmetric arrangement consists of the 2 quadrupoles is called octupole, and so on. So 1 plus 1 is a 2, 2 plus 2 is a 4, 4 plus 4 is a 8. Quarter is a 4, and it is a 8, and so on. Got it, my students? Understood? So if any example, if given the P bar is equal to and the Q is equal to, find the potential means P bar dot AR bar by the 4 pi epsilon naught R square. You can find out the equations also. And the last topic in the third unit, my dear students, the last topic in the third unit, energy stored in the capacitor. Energy stored in a capacitor. Consider a parallel plate capacitor as shown in the figure here. Upward there is a positive charge and downwards there is a negative charge, and in between there is a dielectric constant epsilon, and the direction of the finding of the E bar is in the downwards, and the distance between of these 2 parallel plates is a D, and for these 2 parallel plates we can apply a potential V is equal to nothing but it is a conductor. E bar is equal to V by D. The electric field E bar is equal to applied voltage and the distance between the plates V by D, and the direction is A N bar. Actually the downwards means minus AZ bar is there. We know the Energy stored. In the last class, we derived the expression, the energy stored in electrostatic fields, W is equal to 1 by 2 the volume integral d bar dot E bar into dV. dV is a volume, my dear students, not the potential here. The d is changes as in terms of E epsilon E bar dot E bar. E bar dot E bar is equal to E square, 1 by 2 the volume integral epsilon into E bar square, and E bar is equal to V by D. Okay. E bar is equal to V by D, the applied voltage and the distance between the two plates, parallel plates. Substitute this in this energy stored. W is equal to 1 by 2 the volume integral epsilon into E bar square. What is the E bar? The V by D whole square. V by D whole square. It is a volume integral V. Here this V and this V is not the same. V is here the potential and V is here, it is a volume integral. So 1 by 2 epsilon V square by D square is a constant. So the volume integral dV. Volume integral dV. So volume integral dV is equal to volume means A into D. Okay, my dear students. So volume is equal to the area into the distance. Right, this is a volume 1 by 2 epsilon is the V square by the D square. The integral of the volume integral dV is equal to, the volume integral dV is equal to, actually see here the dq is equal to rho V into dV. You know, the integral q and here the integral of rho V into dV. The charge is there is a charge density. Actually, the integral dou V, not the dou V, dV is equal to the volume integral is a volume, nothing but the area, the surface, and that is a line is there. So totally, it's area into the distance. That is nothing but the volume only. Okay. So A into D. So D and here one of the D's get cancelled. 1 by 2 epsilon A by D into V square. Epsilon 1 by 2 epsilon A by D into V square. What is the epsilon A by D? Is a capacitance. C is equal to epsilon A by D. And the two parallel plates is that is a capacitance. So WE is equal to 1 by 2 CV square. 1 by 2 CV square. The energy stored in the parallel plate capacitor is WE is equal to 1 by 2 CV square. It's a joules. Okay. If the dielectric is a free space, then there is a increase in the stored energy. If the free space is replaced by other dielectric having epsilon is greater than 1. Epsilon R is equal to greater than 1. The free space only, the WR is equal to 1 by 2 CV square. Okay. And energy density, we already know the energy density is W is equal to 1 by 2 the epsilon naught ER square, E bar square into dV, the energy density. In terms of the D is W is equal to 1 by 2 the D bar dot D bar and the E bar. Okay, this already we seen. So with this, the completion of the theory part of electrostatics. Okay.